Our next section is going to be on digital inspection and monitoring technologies. This session is going to be moderated by Fabrizio. Federico is an electronic engineer and he works for AISCAT services, and he's one of the partners of the OMICRON project. Thank you.
Fabrizio.
Sorry, Fabrizio. Okay, you need to keep up of the panelists.
Okay. Thank you, Noemi. Good morning, everyone. In this session, my partners in crime from OMICRON and InfraROB will showcase the results that have been achieved in those projects in the field of digital inspections and monitoring technologies. From the air to the ground, that means what we can expect from now on in the real world for the UAVs, the unmanned aerial vehicles, used for road and critical assets inspections, for cars using a new technology for pavement inspections such as the PointPix, and last but not least for new system sensors, precisely the fibre-optic sensors. So we have a tight schedule. In a moment, I'll leave the floor to the relators, but at the end of the session, we will have a short time for questions for the audience. So getting straight to the heart of the matter, the four speakers are Professor Anibal Ollero. He is a doctor of engineering and professor of robotics at the University of Seville, in which lead also the GRVC robotic lab. And he is, among the others, the scientific director of FADA and Catec in Seville. He will speak about the UAV's inspection of road and critical assets focused on the multi-UAV inspections. The second speaker is Mr. Javier Curado. He has a degree in telecommunication from the University of Seville and more than 10 years of experience. And he worked in robotic, vision and control group of the University of Seville, and now is a senior energy engineer in the perception and artificial intelligence unit at Catec in Spain. He will present the results of the long-range UAV inspections of OMICRON. The first speaker is Miss Hamidreza Alavi. She is a research and teaching associate at the University of Cambridge, specializing in the integration of advanced technologies such as digital twin, building information modeling, and augmented virtual reality. His work bridges the gap between cutting-edge research and practical application, driving sustainability infrastructure solution globally. She will present the PointPix pavement inspection system made in OMICRON. And the fourth speaker is Miss Celina Solari. She has a master's degree in civil engineering from University of Geneva. Currently, she is working as a project manager in research and innovation at RINA Consulting. She's a specialist in managing and coordination European projects. Celina oversees several EU-funded research and innovation projects, driving innovative solutions to enhance the sustainability and resilience of the built environment. So, please come to the stage to start the presentation. Starting from the first speaker, Mr. Anibal Ollero. The floor is yours.
Okay, this first part is dealing with multi-UAV. So I will focus on multi-UAV inspections. So multi-UAV is a topic that we strongly developed in the last 20 years, I would say. So the next slide. Okay, so we are developing this in 20 years. These are 6 projects that I have been coordinating in these 20 years in which we have developed this technology. And a sample is because 3 papers between the 15 most cited ones are from our group. So you can see, for example, just in the last one, the aerial core project that we inspected electrical lines, that we produce only in this paper, in this project, 300 papers, in addition, scientific papers. In addition, we transfer technology to several companies and we generate products. And now these products are running in Europe. Oops. All these complete the background in multi-UAVs, and all of them are European projects in different topics, dealing also with inspection and maintenance, but also in emergencies and so on. Let us concentrate on the topic with Omicron, in which essentially we have a fleet of autonomous. I will reinforce the word autonomous because they are completely autonomous. And they can work in parallel, they can accelerate the process, but they can also obtain different complementary views and increase the resolution of the inspection. So you can see, for example, here, there is a bridge to inspect. We want to inspect over the bridge and also below. So in this, you can see, for example, that the drones, you will see more details later with the next presentations, with camera, communications, and other systems. And then we can have a ground station in which you monitor. They plan the trajectory for all of them, taking into account not only the capacities, basic capacities, capabilities dealing with, for example, the energy, but also the possibility to recharge the battery and also the possibility to take into account the wind, which is very important for the energy. So you can see, for example, here, how there is a monitoring of the full team and how they collaborate. And in this management tool, you can not only launch, but also monitor. But everything is autonomous. Then you can obtain views like this with different degrees of details. And then it is possible to detect different images and collect images, and also even process in real time these images. So you can see these images here, in the bridge, or here you can see details, and you can also look to close views. Even you can enter in very difficult to access sites and obtain images that cannot be obtained by other ways. I have no time to detail here, but in any case, you know the technology. I am trying to introduce the technology. And also, I would like to say that there is some kind of aerial robots that are able to fly, but also to land and to inspect by contact. But this is another topic that I have no time to mention today. So here you can essentially have seen the technology. I think that this technology, we can say that is reliable. This technology is ready to be used, is being used, and I think that we can adapt for the different kind of companies that want to essentially have some constraints and some particularities for the inspection. But this can be also done. So we estimate that the 50% less time needed to develop the inspection. So essentially, we develop a first system that is going to be applied. We can, for example, improve applying real-time artificial intelligence to detect if you learn. Obviously, this needs learning and this needs significant work previously, but this can be applied. Thank you very much for your attention.
Thank you, Professor. Now to speak about the long-range UAV inspections, let's welcome Mr. Javier Curado.
Hello, good morning, everyone. Okay, thank you. In this presentation, we'll be briefly show some of the most important results of the OMICRON project, in our case, in long-range inspection with UAV. And these are some of the main tips. Traffic disruption is reduced because there are no vehicles on the road, for do the inspection. Time and cost of the inspection is lower than with traditional methods. And the processing of the image are always the same, so the susceptibility to human error is out. And also we have a huge data set of data of image from the raw in this case. So we have been working with a custom UAV with 2 different line of works. The high quality camera is for the road inspection, and the another 4 cameras are for the long range, because when you are flying beyond visual line of sight, you have to be airspace observers in ground, and if you don't have these people, you need a system to monitoring the environment. So you will see this in the next slide. And this is the reason for the top cameras. So in this case, we have been testing in Puliana and Setifonti, and with the UAV. These are some picture of the camera, of the high quality camera. And the last part is the photogrammetry model of the viaduct. We have 6 millimeters of precision of the data. In Puliana is more or less the same. This is the reason of the top cameras of the UAV. This is a subject, the perception of the airspace observers is difficult to see where is the drone, where is the possible threat. So it's better use an onboard device and process this information. This is the test of the detect and avoid system with the UAV and ultralight craft. And we test flying more than 1 kilometer. There are some data of the inspection. And this is the whole system working. So we have the 4 cameras, and while we are inspecting or monitoring the environment, we are taking picture every 6 meters of the road. And then you get the earth mosaic, doing the photogrammetry and the point cloud. I don't know if some videos is playing or not. Yes, no. It's, the avoidance maneuver when you see the threat and you go down the height of the UAV, and when the graph is as passed, we return to the original mission. And the next actions are, one of the most interesting is increasing the battery efficiency in order to get more distance. The same with the second bullet point is using lighter and smaller device to get more efficiency and get more distance. And the use of solutions like drone in a box to do regular inspection, because this is a box that you can put in some place with electricity and internet connection, and autonomous do the inspection that you have programmed. So it's very interesting. We have some projects with this type of device now. Obviously, the last, not the least, because the regulation in the operation of the UAV are very restricted, and it is too difficult to fly long distance. It's very, very difficult. It's about 6 months to get the permits to fly long distance. So this is one of the most restrictive points. I think that this is all. More question or? Thank you so much.
Thank you, Javier. Now, to speak about the PointPix pavement inspection system, please welcome to Mr. Hamidreza Alavi. The floor is yours.
Okay. Hey, everyone. I'm Hamid. I'm really happy to be here. Maybe a tiny part of the OMICRON project. And today I'm just going to talk about the PointPix system that we developed in Cambridge. In Cambridge, the focus for us is to cut down the price to be eligible for every authorities to use this system in their professionalism. I mean, if they want to use it for the roads, for the bridges, or for whatever they have it for the purpose. So in this case, we need to design this system from the scratch. Every sensor that we are considering in this case, it should be designed by the designer, and also not only the software, the hardware, but also the software should be developed to optimize the cost in this case. So our aim was to actually cut down the price by 50% for the inspection cost, and also 30% faster inspections. We have implemented 2 demos in this case. One is Puliana in Florence, which is the route length is less than 1 kilometer. Maintaining that equipment, which is quite easy, it's based on the design that we have developed. You can simply maintain it on the roof rack on the car, and it just takes 1 minute to mount it. And then you can see that less than 1 minute it takes to inspect the area. And we gather the data like this. So the point cloud data we capture is like this. The second demo is the Setafonti, again is the Florence, but this time is around 2 kilometers. The mounting line is the same, but again you can see that less than 1 minute we can capture the point cloud data in this regard for the roads. And this is the data we already captured. But you might probably ask which piece we can capture this data. This is really important because when we go faster, the less data we capture. So it's like we implemented with the 30 kilometer per hour till 80 kilometer per hour. So as you can see, the more we go faster, the less point cloud data we capture. But it doesn't matter because we're going to focus on the mapping data for us. So in this case, it works properly. But as you can see that the 30 kilometers, we can capture around 7,500, and in 80 kilometers is around 3,000, almost half. So if we want to be more accurate, we should definitely go a little bit slower. What's next? We're going to consider 2 aspects in this case, considering what we've learned from the OMICRON project. Is that we're going to have 2 aspects. The first is the cheap course inspection, and the second one is the affordable fine inspection. And when I'm saying cheap course inspection and affordable fine means that we need to have different kind of HD cameras, mid-range LiDAR, accurate GNSS, and on the other hand, we also need multi-LiDAR, multi-camera, highly accurate, and we're going to have the fine inspection in this case. But we normally are developing some other things like this that if we have the camera, if the recent cars have the camera installed on their own, we can use this data to capture all this kind of stuff and then try to provide it to actually reuse these HD cameras on cars and try to provide the fast initial inspection for defects. The other thing that I just wanted to mention is that we are currently developing this kind of stuff, image scanning for the for the coarse inspection and also LiDAR for the scanning for the fine inspection. That's all from my side. If you have any question at the end of the session, I'll be happy to help you out. Thanks.
Thank you, Hamidreza. And now to speak about the fiber optic sensors, please welcome to Ms. Celina Solari.
Good morning to everyone. I'm Celina Solari from RINA Consulting, that it's a large engineering consultant company based in Italy, and I'm very happy to be here. And today I will present you a session focused on fiber optic sensor developed within the InfraROB project. So between the InfraROB innovative technological solution, there is a solution for the long-term damage detection of pavement, relying on the integration of distributed fiber optic sensor in asphalt, and also an automatic lay-down system for it. This kind of monitoring system can be used for road maintenance optimization because it helps to identify with high precision, about 10 centimeters, where damage are occurring to the pavement, damage like a crack with at very early stage. So the data that can be collected through this system can be useful for decision-making process, because in particular to tailor the size and the time of intervention, which is a very important aspect in helping in optimization balance between benefit and cost of maintenance. So the main goal of this solution that need to be fulfilled, that need to be achieved for the fulfillment of the InfraROB project are the following. So first of all, the capability to withstand the automatic laying process that stress the cable during the laydown. The capability to withstand the asphalt pavement realization process with achieve high temperature and can also damage the asphalt due to the aggregates. The validation of long-distance application for this technology, and also the integration of the data collected within the InfraROB dashboard for the pavement damage detection monitoring. So this fiber optic technology can provide integrated sensing with extensive measurement lengths, offering unique benefits such as small dimension, lightweight, long-term stability, also corrosion resistant, electricity passivity, immunity to the electromagnetic and radio frequency interference, and also the capability of intermittent readings and also the interconnection between these readings. So this characteristic the characteristic of this solution can match the requirement defined within the InfraROB project for the monitoring system. So this kind of monitoring system that is embedded in the asphalt automatically was designed following four steps. The first one was the commercial the selection of commercial fiber optic sensor that needs to fulfill some requirement related both to the mechanical strength and also to the temperature. The following survival test of this fiber optic cable to the asphalt production and compaction processes, and also the interaction of fiber optic cable with the asphalt by means of petrology asphalt test. And finally, this fiber optic cables was validated from a mechanical point of view through some flexural strength test. Okay, here you can see some picture of a first activity related to the validation of this system that was conducted in a Brussi facility in Italy, Nervesa della Battaglia. In this first activity, both the sensor was embedded in the asphalt manually before the asphalt laydown. This because during this activity the main objective was to make a further validation of the survival of the fiber optic sensor before the asphalt process. So during this activity, both strain and temperature acquisition were collected. Both these value were monitored during the asphalt laydown process, and both this kind of sensor was embedded in the asphalt. In this way, we could also see the advancement of the asphalt process upon the sensor. Here you can see the picture of the main validation activity that was performed in InfraROB demo. In a 200-meter segment in an Austrian highway in Springfield. And during this process, both the sensor, the strain and the temperature sensor were embedded in the asphalt automatically during the laydown system. And both the cable survived to the mechanical stress during this process. In particular, we collected during this activity some acquisition for temperature and also for strain that can be useful for the future to evaluate some damage and reveal some cracks in the asphalt. Unfortunately, the time of the project is not enough long to permit that this system can evaluate some damage during the time of the project. But during this test, we fully demonstrate, the technology and the survival of this cable during the process. Here you can see a screenshot about the data that we collected during the activity, and we integrated in the InfraROB dashboard and so in the InfraROB database. And so, as demonstrated before, all the goals and the objective of the InfraROB project that we showed before have been achieved, and so the capability to resist to the automatic laydown process, the capability to resist to the asphalt pavement realization, and also long distance application. So this is all from my side. Thank you very much to everyone.